Hey gang, and welcome to another exam solutions walkthrough for the practice exam, Organic Chemistry 1, Exam 2. So, gang, if you are here, that is probably because you are gearing up to tackle an exam consisting of stereochemistry, substitution, elimination. So, if you're looking for answers based on, tackling the practice exam, you're in the right place. So we will do all things practice test for, this material. So, enough of my blabbering. Let's get after it. Okay, gang, to kick off this practice exam in problem 1, you have to identify where the stereocenters are in this lovely molecule. I've already done that. And you need to assign RNS for those stereocenters that you will identify, and I've done that as well. So just gonna go quickly through, and if you're confused at any of them, I'm gonna try and just do a very brief, here's why it's R or here's why it's S. So if we take a look up here, I hope you're seeing not a stereocenter, not a stereocenter, right? Because to be a stereocenter, we need to be attached to 4 unique things. So right here, I hope you're seeing our lowest priority group of hydrogen is facing away from us. Clearly, we have this ethyl group, we have an OH, and then we have the rest of this giant thing. So this is, in fact, a stereocenter. So priority would go 1, and even though we have a carbon tie here, we have a double bond down here as well as just being attached to a nitrogen. So 2 right there. 3, really quickly, you can see we are turning left, which means S, and our lowest priority group is facing away from us, so that is our configuration. So I hope you're seeing no stereocenters in here. This is not a stereocenter as well. We'll talk about that amines way in the future. sp2 carbon, so not, we know that geometry is trigonal planar. So we get to this carbon right here, and I hope you're seeing that there's, this is secondary, there's 2 hydrogens not drawn there, so not a stereocenter. However, when we get to this carbon right here, you can clearly see we definitely have 4 things drawn as well as a hydrogen not labeled. Lowest priority group is facing towards us, so we definitely have a stereocenter. We need to figure out the priority though. And so you can see we have a bunch of ties, and in fact, 1, 2, 3, and then we have something attached to an oxygen. We have 1, 2, and then this carbon's attached to another carbon with a double bond. And then we have 1, 2, and this carbon's attached to a nitrogen. So in fact, this is priority number 1, this is priority number 2, this is priority number 3. So we look like we are R, but in fact we are S because the lowest priority group is facing towards us. So you can see how that is S. Down here, I hope you're seeing, I'm going to clean some up a little bit because this is getting a little crowded. Down here, we have a nitrogen right there, directly attached. We have our lowest priority group facing away from us, so we just have to assign. So the amine gets priority number 1, and then you can see we have an interesting carbon tie we need to break here. So these 2 are equivalent. Then we go up to here, but the carbonyl wins down here. So this is 2, this is 3. You can see our arrow goes like this. We're turning left, which means we are S. Then moving right along, we see this is a stereocenter right here. Lowest priority group is facing away from us. So you can see we have 1, 2, and then an oxygen, 1, 2, then an oxygen. However, we are double bonded there. So priority 1 goes this way, priority 2 goes this way, methyl group is priority 3. You can see we are turning to the right, lowest priority group is facing away from us. That is why we are R. I can leave that. So then we have 2 stereocenters right here. So I'm going to clean up a little bit because, again, getting a little crowded up in here. So obviously the oxygen gets priority number 1. This carbon's attached to an oxygen, it gets priority number 2. This area gets number 3. Lowest priority group is facing towards us. So we'll assign and take the opposite. Looks like we are going S, but in fact we are going R. Makes sense. So again, I'll clean this up because we have to assign next door. Almost done. So our lowest priority group here is the methyl group actually, so it's facing towards us. So you can see again, priority number 1 goes to the oxygen, priority 2 goes over here, priority 3 goes up here. So we look like we are R, but lowest priority group is facing towards us, that's why we are S. Last but not least, right, if you're wondering why this isn't a stereocenter, well, we're attached to 2 methyl groups. We need 4 unique things. That's not the case at that position. So, right here, lowest priority group is facing towards us. Just trying to save my red marker, gets all icky when it gets in the black. So, alcohol goes number 1, and then you can see we have a tie here, and then when we go here, this group wins, so 2 and then 3. So we look like we are R, but in fact, we are S. So that does it for problem 1, gang. If you're confused, just really take it slow. You know, illustrate how to break ties like we've done before. I just kind of wanted to go fast so this video doesn't get super long. And as I say that, let's move on to number 2. Moving on to problem 2, we have a series of true-false statements, and I picked these and or I crafted these because I think there can be a lot of confusion around, you know, explaining and using the terminology of stereochemistry, so I wanted to set that straight in this section. So if we look at A, a molecule has a non-superimposable, a chiral molecule has a non-superimposable mirror image and is optically active. True or false? I hope, you know, you say this is true because this is just the definition of chirality. If something is chiral, right, that means it has a left and right hand pair that, you know, if this is the molecule, right, this is its mirror image, but you can't superimpose it. You can't put it directly on top of itself and it be the same. They're inherently different. And if something is chiral, right, if you have plain polarized light, meaning if you shine light through a filter that makes it then just go one wave, if it hits a solution of that chiral molecule, it will bend one way or the other. So that's just the definition of chirality. A is true. So a molecule is always chiral as long as it has one or more stereocenters. This one I feel like could be the most confusing, but false, okay? Because something, and I'll give you an example. If you have something like this, methyl and methyl, gang, this is a stereocenter and this is a stereocenter. However, this molecule has a plane of symmetry. And when you have a plane of symmetry, you are not chiral. This is what is called a mesostructure. And we've talked about that before. So just because you have stereocenters does not ensure chirality. You need to not have a plane of symmetry in your molecule. Okay, so a mesostructure has an enantiomer. So this kind of goes along with B. So this is false. If you are meso, you're symmetrical. So if I wanted to draw the enantiomer, if I tried to draw the enantiomer of this structure up here, it would look like this. However, because there's a plane of symmetry, what I can do is if I flip this structure over like a pancake, it's going to look exactly like this. I can then superimpose them and they would be the same. So it fails the definition of chirality. There's no mirror image, right? And a mirror image is an enantiomer. D, enantiomers and diastereomers are 2 types of stereoisomers. Again, a definition, right? It's you know, these are the 2 types of stereoisomers. Racemic mixtures exhibit a net optical activity. So racemic mixtures, remember that's when you have 50% one enantiomer, 50% the other. So we did talk about how chiral structures, you know, when you have a solution of a chiral structure, it will bend the plane of polarized light. However, if you have, you know, enantiomers have the same properties, but where they vary is that they bend the plane of polarized light in different directions in equal amounts. So, will a racemic mixture exhibit net optical activity? No, it's going to have 0 optical activity. Both structures, so false, they will counteract each other completely and equally. Okay? That's 2, on to 3. Okay, gang, in problem 3, we have 4 structures, and all we're trying to do here is determine the relationship between them, right? This could be a stereoisomeric relationship, it could be a structural, you know, isomeric relationship, it could be the same molecule, you know, we just have to use stereochemistry and our knowledge to find out. So if we take a look right here in problem 1. So I was being sneaky, I gave us some chairs, but I know you're too smart for this. If you take a look, the first thing you would need to kind of ensure is, are these chlorines in the same place on this structure? And sure enough, they are a 1-4 relationship. Right? If this was 1-4 and this was 1-3, you could just stop right there and say structural isomers, because they'd have the same molecular formula, but we would have different bond-to-bond connections. Okay? But we have the same, you know, we're hooked up the same structurally, so this could be a stereochemical difference, or could be the same structure. And if we really quickly just convert chair to bond line, you know, this is position 1, our chlorine's going up here. At position 1, 2, 3, and 4, chlorine's going down, so we look like this. And if we do the same over here, I think what you'd see is we're up, equatorial up, but still up nonetheless. And at position 4, we are equatorial down. This is a classic case of same structure. Okay? Moving on to 2, or B. So we definitely should, so if we take a look, right, we can see, okay, methyl, OH, hydrogen, methyl, OH, hydrogen, ethyl, methyl, hydrogen, ethyl, methyl, hydrogen. We're hooked up structurally the same here, but we need to evaluate stereochemistry. So if we take a look here, you can see annoyingly we'll have to double switch here. We'll have to double switch there as well. But if we take a look here as far as priority, you can see we're going to have a carbon tie here as well as a carbon tie with the ethyl. And this will win out this side because of the bond to oxygen. This will be number 2. The methyl is number 3. So our lowest priority group is facing us. We look like we're S, but we're actually, in fact, R. So I'll erase these little numbers. We'll have to do a slightly different approach over here. I'm just going to break this out over here. So what I'm going to do is I'm going to go ahead and switch the OH and the H just to get that facing away from me. And then I'll need to switch one more time. So what I'll do is I'll put the OH over here, and then I'll put the methyl over here. So this is my double switch. Okay, so the oxygen gets first priority. This part over here will beat out the methyl. Methyl comes in third. So in fact here, we look our lowest priority group is facing away from us. We are R, okay? So let's play the same game over here. We'll start here because it's easier. 1, 2, and 3. We look S, and in fact, we are S. Okay, I'll erase this because we will need to double switch. So if we take a look here, I'm just going to break this out over here and just kind of draw this carbon. So what I'll do first is I'll switch the hydrogen and the ethyl to get the hydrogen facing away from us. So that's a single switch. And then I will very quickly switch the ethyl and the methyl. So this right here is our double switch. So again, what we need to do, priorities stay the same, which is nice. So this is 1, this is 2, and this is 3. 1 being, this that I didn't redraw. We look R, and in fact, 1, 2, 3, we are in fact R. So this is R right here. So we can erase this. So you can see, gang, we aren't completely opposite, right? For this to be an antimerge, we would need this to be SS. We are RR, and then we are R, we're something else that's not opposite. So that means we are the one word that is super hard to say in OCHEM, distereomers. Okay, stereoisomers, but not complete mirror images. Okay, so over here, one thing you should check is the amount of carbons. 1, 2, bromine at 3, 4, 5, 6, 7, 8. So we have a bromine at 3 and 6. Over here, 1, 2, 3, 4, 5, 6, 7, 8. So we have 2 bromines in the same location. We have 2 wedges over here, 2 dashes over here. But I hope you are saying, Joe, stop. We don't need to talk about this anymore because there's a plane of symmetry. So we have 8 carbons, and if we draw a line completely down here, I drew the carbons wacky, but they don't have, in reality, it doesn't matter how you draw them, how you, finagle your spaghetti monster, right? There's a plane of symmetry here, and there's no other way around it. So it doesn't matter that this is in fact a stereocenter, and it doesn't matter that this is in fact a stereocenter, right? These are the same structure because this is a mesostructure. Plane of symmetry, right? So when you're meso, you do not have a mirror image, you are just the same. So I wanted to put a meso situation on there as well. So if we look down here, we see we just have one stereocenter, and of course I had to throw in a Fisher projection because they're just too fun to skip, right? So remember our conventions, the arms come out to hug you, the top and bottom are going away from you. So if we take a look here, bromine's priority 1, the OH is 2, the methyl is 3. Lowest priority group is facing us. So we look R, but in fact we are S, because lowest priority group is facing us. We have to take the opposite. Over here, it's the same deal. 1, 2, 3. So we look S, but in fact we are R. So we are opposite at the one stereocenter we have. So this is a classic case of enantiomers. Okay? So I hope you had no issues getting these relationships down. I tried to put, one of each. I did skip structural, but oh well. So that does it for 3. On to 4. Okay, gang, for the first part of part 4, we have for substitution elimination reactions. Our job is to identify what kind as well as complete that bad boy. So if we take a look at the first one, remember our checklist. You have to think about the status of your leaving group, the fact if you've been given a good nucleophile or a good base, the degree of your substituent carbon, whether it's methyl or primary or secondary or tertiary, and solvent, right? So if we take a look here, polar aprotic solvent, so thinking not forming a carbocation, so probably in the SN2E2 lane, we have a primary carbon and something that's, an okay nucleophile. So this, to me, looks like SN2, okay? Especially because primary, and we don't have a super strong base. So remember, the thing we'll have to worry about, make sure we take care of, is that this is a stereocenter, so we need to invert our stereochemistry, attack from the backside. So we have O, we have this methoxy nucleophile, we will attack, our good group Cl- will get out of town. So what we can do is, if we were going to, here's the trick I like to do, is we know that our priorities, if we were to number them, look like this. So what we can go ahead and do is the group we are attaching will be the same priority as our leaving group. So if I draw it just like this and swap out the leaving group and the nucleophile, this is the exact same stereochemistry. And if I want to just be lazy but correct, let me just do a single switch. I'll put the deuterium here and I'll put the hydrogen there. And just to prove to you that the stereochemistry got inverted, our lowest priority group is facing towards us. So while we look like R, we are in fact S here. And if I go over here, still we are 1, 2, 3. We look R, and we are R because hydrogen is facing away from us. So remember, R and S is always there for you to fall back on. So if you need to invert stereochemistry and you're not quite sure, just assign it. And if you ended up doing the same exact stereochemistry, flip 2 groups, and then you are golden. Okay, moving on to this problem. So I hope you're seeing good leaving group in bromine, polar protic situation, as well as being tertiary. This is screaming SN1. We are going to, and we don't have heat, so it's not going to be, an E1 favoring product, right? This is just going to be SN1 with a minor E1, so we're just going to draw SN1. So, right, remember, this leaves. We should check to see if we're going to have any carbocation shifts. Fortunately, we do not. So if we continue forward, what we got then, we have our water attack, and we don't have a stereocenter here, right? Because, and I'm going to just skip the cleanup step, but this is not a chiral center because we are not attached to 4 unique things. These are 2 methyl groups. So no worrying about reflecting your racemic mixture. You can just draw straight lines. There's no stereochemistry involved in this problem. So if we go here, what I hope you're seeing, right, we have this tosylate leaving group, good leaving group. We are 1, 2, 3. We are tertiary, and we have NH2-, super strong base. No solvent here left off, but I hope you'd see there's enough here to say, okay, this is absolutely E2. Okay, sometimes, people don't include a solvent, but this is screaming E2 from the other clues we have available to us. So remember, the thing we have to worry about here is the anti-periplanar requirement. Our leaving group is up, so we need the hydrogen to eliminate to be down, right? Break out that party dance move. So remember, this is a small base, so we would ideally want to make the Saitsev product, the most substituted double bond, right? However, and then that would be going this way, right, to this tertiary carbon here. However, the hydrogen there, we have a cis-periplanar situation, right? We're both up, and that's no good. So we can't do elimination there. We have to, remember, we could, rotate bonds in a, linear situation, but in a ring, up is up and down is down, and that's the way it is. So this is the elimination we have to perform right here. So we have NH2-, we eliminate the H, electrons swing down, leaving group leaves. So when you draw your product, make sure, if anything is now sp2, those better be flat lines you have drawn off of them. So we have this right here, that ethyl group didn't get touched at all. This methyl group, we have a double bond here now, so this methyl group needs to be a straight line. And that is your elimination product. Okay, so down here, secondary carbon with a good leaving group. we have Br-, which we know is a terrible base but a great nucleophile. And we have HMPA, and I forget what that stands for, but I know it is a polar aprotic solvent. So even though we're secondary, which could be that iffy situation, all signs are screaming at SN2, and luckily this is a really cut and dried one. Just come from the back side, kick it off, and nicely enough, you just need to, extra carbon, don't draw an extra carbon, attach that bromine as a dash. Okay, that's part 1. So let's do part 2 of 4 and keep chugging along. Okay, gang, to round out problem 4, we have 4 more lovely mystery substitution and elimination problems, so let's identify them. So if we look at problem 1, I hope what you're seeing right off the bat, doesn't even matter if there's a solvent, you see LDA and you know for a fact, without a doubt in your mind, you bet your life on it, that is going to be E2. All right, so we see E2 there, we see our good leaving group, and we know that this is really an exercise in doing a Hoffman elimination. So we are forming that least substituted double bond. Because clearly we could have a secondary tertiary double bond, right? That would be a tri-substituted double bond, but we are going to opt for the di-substituted double bond because, and we have both hydrogens here, wedge and dash, so no worries, even though this is the one, the dash we want to work with, because we are big and bulky, and that's the easier hydrogen for LDA to pick off, the easier proton to abstract. So, this is not correct arrow pushing, but it's just rough. This is what we will do. We will then form a double bond right there. Here, I'm going to draw an arrow up there. And then remember, don't change anything else about the rest of the structure. We got the double bond there. We have the wedged methyl group up there. And that's all she wrote for that one. Okay, so down here. So, I'm going to break it down, but then I hope you're going to see what is really actually going on. So we have I-, really good nucleophile. That's, bad base. So this is already shaping up to look like SN2. We have a polar aprotic solvent. So even just from this alone, if you didn't even show me this, right, it's screaming SN2. However, because this is a terrible base, this will not do E2 for you. And since we're polar aprotic, we're really dealing with SN2 and E2. But if we look here, this carbon, our substrate, 1, 2, 3. This is a tertiary carbon. We can't do SN2. So, we would try to do SN2. I'm going to write it, but I'm going to cross it out because, in fact, gang, nothing happens here. No reaction. Because this can't do elimination for you. It's too weak of a base. And that's the only option we have when it's tertiary. A tertiary substrate. We do have a good leaving group, right? Polar aprotic, but it's the wrong tool for our situation. So, no reaction. Down here, I hope you're seeing, okay, tertiary carbon, good leaving group, polar protic. This is screaming SN1. And I hope you're seeing we have a carbon that is a stereocenter. We're going to keep our, we're going to have a stereochemistry in the product. We have to reflect a racemic mixture here. But before we do anything, we'll show this leaving. I will draw the carbocation we produce. Oh, I hope you can see this mistake I just made. Planar. So, that's what we'll have. And then ethanol will attack from on top and on bottom. So, our product, you can represent this a few ways. So, obviously, keep that methyl group wedged down there. We didn't touch that methyl group whatsoever. We have a wedged methyl group up top and a dashed OET. You can either do plus, actually, can't write plus an enantiomer. Almost made a mistake. All right, and I'll explain why. But make sure you draw both products. The reason why you can't draw plus enantiomer is because the enantiomer of this would involve changing the stereochemistry of this down here, but that's not what this reaction does. So, you must reflect both products here. They are not enantiomers. They are, in fact, diastereomers because we only differ at our stereochemistry at this position right here, not the square position. So these are not enantiomers. They are diastereomers, okay? So, down, last but not least, we're seeing hydroxide, we're seeing acetone, we are seeing a primary substrate, and the only time I feel like this has happened on jOeCHEM, we have a bad leaving group. This is our big no-no halogen. If we try to kick off this, we are kicking off F-, and that is not a weak, stable base. That is strong as hell. So, no reaction. Bang. Ladies and gents, that is number 4. Let's finish off exam 2 with number 5. Okay, gang, to round out exam 2, in this problem, we have reaction A and reaction B. We need to pick the faster, more favorable reaction, and then we need to draw its mechanism and explain why we are, for our choice. So I hope, we've seen, maybe this exact same problem a few times on jOeCHEM, but if we take a look here, I hope what you're seeing is 2 reactants going to 1 product. Here we're seeing 1 to 1. So this is intermolecular, between molecules. This is intra, within. So the more favorable, faster reaction, reaction B, the mechanism goes a little something like this. It's quick and dirty. Make sure I drew enough. 1, 2, 3, 4, 5, 6. Yep, we're just going to wrap around, attack this carbon, boot off chlorine, and if we number our carbons, 1, 2, 3, 4, 5, and yes, oxygen is in the ring since it's making a bond to carbon. Just a one-stepper, a beautiful thing. That does it right there. So, again, for the explanation, we can say for A, we have, let me do it this way. For A, we have 2 reactants going to 1 product. And for B, we have a 1 to 1. 1 to 1. Now, do not forget, from our thermodynamic days, delta G equals delta H minus T delta S. So remember, we ideally would love a negative delta G. That means our reaction is spontaneous, or gives free energy, right? Negative is good. Negative means it's spontaneous, it's going to happen. So, we can't, hardcore do some number analysis here. We'd have to look up the bond energies of what we're breaking and what we're forming. However, I won't flinch again, freak out. But if we can change, if we can compare one thing, the entropy of these reactions are inherently different. So remember, entropy, a measure of disorder, right? You ideally want to go from fewer reactants to more products because that means in your mixture, you have more things, more variation, bouncing around, hitting walls, hitting each other. That's chaos. That's more disorder. We want more to move from less to more. However, up here, our system gets more ordered. We go from more reactants to fewer products. Here, we stay the same. So you can say that the delta S change here is relatively 0. However, up here, it is going to be, for entropy, a bad entropy is negative. So you can definitely say that the change is going to be negative. So the entropy's bad up here. It's relatively neutral up here. So because of that fact, this is the reaction that is more favorable. Intermolecular takes it for the win. Okay, gang, that wraps it up for exam 2. If you're watching this video, that means you've supported jOeCHEM financially, and I'm thankful you're using the site and the fact that you paid money and supported the website. I can't thank you enough. I hope this is the tool you were looking for in terms of helping you conquer carbon. I'm so happy you're using it right now. I hope you're using it toward the end of your organic career. But no matter what, I hope to see you all in the next video.